All right, let's look at these banked curve videos or things. All right, now the only thing on a banked curve, the statistical friction force provides the centripetal force. It's the static frictional force that's pushing the car towards the center. All right. Okay. All right, and so that's what's pushing the car towards. So in other words, on a bank static frictional force. So let's take a look at this little video here. All right, so we're moving along. Static frictional force mu of s times f of n. All right. So here we go. Initial velocity. So
a car following an unbanked curve makes use of static friction force to provide the needed centripetal force to stay on the road. The static friction force is limited to a maximum value depending on the normal force of the road on the car and the coefficient of static friction. The centripetal force needed to keep the car on the curve depends on the car's mass and speed, as well as the radius of the corner. Run the simulation with the coefficient of static friction set at 0.9, corresponding to dry pavement. Click Start to enter the curve. The friction force was sufficient to keep the car on the track.
Okay, so the centripetal force, if this gets too big, then what happens is you need a bigger radius for the car. If the velocity gets too big, then you're going to need a bigger radius to equal the centripetal frictional force, which keeps it on the thing. So let's up the velocity. Now hit start play.
The friction force was sufficient to keep the car on the track.
That's because that coefficient of static friction is so big. Let's up it again. What? I don't know why they had to get so dramatic.
The available friction force was not enough to keep the car on the track.
Okay, so what do I have it at? 22 meters per second. Mu of s is 0.9. Let's calculate that. Right. And notice what happens.
The available friction force was not enough to keep the car on the track.
Notice what happens too. Even if I lower if the coefficient of static friction, when it gets icy outside, look what happens.
The friction force was sufficient to keep
the car
very
on
slow. The track.
I speed up just a little bit. It keeps raining, or icy, and I speed up just a little bit. Very, very small coefficient of friction because it's icy.
The available friction force was not enough to keep the car on the track.
So I kind of like that. So let's take a look at what was going on. So the frictional force. So you're going around a curve, all right? And here's your centripetal force, MAC, which is your net force, all right? Which is your net force. So the sum of the forces in the x direction is equal to MAC, you're going to make that turn within that radius, all right? And then the only other force that's working here, is equal to, this is minus, so it's f of x. I don't know why I could have done it there. Is f max of the static frictional force, which is equal to minus mu of s times the normal force. So I can cancel out my negative signs. I could have done it the other way. Because that's the only force that's acting on it. And if it exceeds this, then you're going to crash. Does that make any sense? All right. So if this turns out to be larger than this, see, this is constant. That's not changing. But if this turns out to be larger than this over here, then your car is going to go off the road. All right. out here. No.